Okay, so now we are going to look at an empirical example, a famous paper by Anguis and Kruger. So in the literature, there's a famous bias called ability bias that comes from return to education, estimating return to education, right? Typically, economists want to estimate the return to education. We request earning or wage on 8 years of education. And a typical regression looks like this, right? Log wage is a function of education, and beta 1 is return to education. However, because we know there's some correlation between education and the error turn. For example, we call that ability. For example, smart people tend to have more education. Smart people also more like to earn more, but that could be because of their smart, not because of their education. Right. In general, ability can mean ability could be also IQ or motivation or even family connection, right? So it's just essentially that's just everything not in the regression, and everything not in the regression, not control in the regression, but also affect both education and wage. And we know there's omitted variable bias because we cannot control for ability, right? Sometimes people try to put control for IQ or standardized test score in the regression, but that won't be able to capture all the ability. For example, like motivation or family connection. So we know that there's likely to be some bias in the OLS estimates of this kind of return to education estimates. So people try to find some instrumental variables. Some people use parents' education, the number of siblings, or the distance from the nearest university at age 16. Okay. And so obviously, like for example, like parents' education is probably also endogenous, actually pretty endogenous, right? We know parents' education is a strong predictor of children's education. However, parents' IQ and children's IQ probably also highly correlated. So it's also likely to be very endogenous. The last digit of social security number is also from Angus. It's a so that's from one of his papers that because during the Vietnam War, the U.S. government did a lottery every month. If your last digit of social security number matched the lottery number in that month, you are more likely to be drafted. You only have 3 options. You can either go to Canada, go to jail, or you can go to university. So Angus finds that actually if so those lottery winners, they tend to have a higher education, and therefore we can use this social security number as an instrument. The last one is quarter birth, which we are going to talk about here. And note that, right, so right, so these are strong, these are strong, so these are stronger instruments, these are weaker instruments, but these tended to be more, but stronger instruments tended to be more endogenous. Okay. So there's apparently it's not very easy to get a good instrument. Right. So like The social security number and quarter of birth are nearly random, but they are actually pretty weak instruments. So let's talk about quarter of birth. So why do quarters of birth can be instruments? So in the U.S., there are compulsory schooling laws that allow students to drop out at certain age. So like in some states, when a student reaches 16 years old, he or she can drop out legally. In some other state, the legal dropout age is like 17 years old. And we know that people born in the first 2 quarters are older than the people born in later 2 quarters. So people born in the first 2 quarters tend to have lower education than people born in later 2 quarters because they can drop out earlier. And because quarter of birth is nearly random, so we can use these people's quarter of birth as instruments. We need to show whether quarter of birth actually predict education. Okay, and the Angus-Kruger shows that in the figure here, right? So, the x-axis is years of birth, and the y-axis is years of education. There is an increasing trend because younger people tend to get more education. However, we do see that people born in the first 2 quarters tend to have lower education than people born in the 3rd or the 4th quarters. If we remove the upward trending, that becomes even more obvious, right? The people born in first 2 quarters tend to have lower education than people born in the later 2 quarters. And this is basically the first stage relationship, right? This is the first stage regression. We are not doing a regression, but we are already showing there's a first stage relationship between quarter of birth, the instrument, and the and education, the endogenous variable. And here we plot the quarter of birth with log weekly earnings. Again, there's a downwarding trend because younger people earn less. But if we look at like people born between 1930 to 1940s, we do see that people born in the first 2 quarters tend to have lower earnings versus people born in the later 2 quarters. And this is the reduced form relationships, right? So we show there's indeed a relationship between the instrument, an empirical relationship between the instrument and the outcome variable, log weekly earnings here. Right? Remember, an IV estimator is the ratio of reduced form over first stage. And Angus and Kruger already showed that the first stage, both the first stage and the reduced form seem to be very strong. If you look at the paper, you should read the paper. You can see that the relevant estimates in both the first stage and second stage regression are indeed highly statistically significant. And they show that the return to education is around 0.8 from 2-stage least square and 0.6 from the OLS. Just to keep in mind that the finding is somewhat surprising because we thought the OLS estimates are upward bias because of the ability bias. But somehow they actually find that the IV estimates is larger than the OLS estimates. And in fact, that's very common in the literature. I would say 95% of time, the IV or two-stage least square estimates tend to be larger than the OLS estimates. We are going to discuss why is that a bit later when we talk about local average treatment effects. Okay, now let's focus on the weak IV problem, right? So the weak IV problem. So Baum and Al 1995 paper criticized Enquist and Kruger paper. They argue that the results from Enquist and Kruger are likely to be spurious because of weak instrument, even though they have a very large sample size, about 330,000. Right, that's huge. So the first problem is quarter of births is the first problem is quarter of births is very weak. Even though quarter of births predicts education, the relationship is extremely weak, with a partial R square only around 0.01%. So that means any small endogeneity can cause huge inconsistencies in the IV estimates. Okay. And there is some research showing that people born in first two quarters are more likely to have a teenage parent. And why is that? So the reason is in the North Hemisphere, teenagers may have sex during the summer. 9 months later, they will have baby. So people born in first two quarters are actually more likely to have teenage parents. Of course, this is very small proportion of people, but people who drop off high school because of they were born in first two quarters are also a very small proportion of students. And we know that, so even if there's only a small or tiny endogeneity problem from this IV, because the predictive power is also very weak, there's no guarantee that the IV estimates from using quarter births as instruments are necessarily better or more consistent than the OLS estimates. A second issue is finite sample bias. You may think, well, with the huge sample size here, finite sample bias shouldn't be an issue. But like we discussed before, we never really know how large is large enough, right? The asymptotic analysis doesn't really tell us how large is large enough. And we know that IV estimates are biased in the finite sample. And Baum and Al, they actually show that they use a very clever way to show that they use Monte Carlo simulation, and they generate some randomly generate fake instruments which have zero explanatory power, and they show that instead of so the two-stage least square estimates using fake instrument should have a return to education of 0. But they show that that's actually not 0. It's actually very close to the IV estimate reported by Enquist Kruger, which suggests that the IV estimates in Enquist Kruger could be driven by finite sample bias. So this is a table from Baum and Al, but this is exactly the same as those reported in Enquist Kruger. So they just replicate the findings in in Anglerson-Kruger. So first of all, you can see the OLS estimates in column 1, 3, and 5. They're almost identical. They're basically identical. The reason is because it's very efficient and the standard error is very small. In column 2, we use quarter burst as instrument. There are only 3 instruments. The first quarter, second quarter, and third quarter. The fourth quarter is the omitted group. In column 4, they interact with quarter burst with year of birth. So they have 10 years of birth. So we have 30 excludable instruments. In the last column, because they control for age and age square, that drop 2 instruments, so that's become 28 instruments. Okay, so note that. So first of all, let's see. So remember the first problem we discussed about the IV estimates is that IV estimates is less efficient and has larger standard errors. One problem is that you may not be able to distinguish the OLS estimate from the IV estimates, even though the point estimates could be different. But their confidence interval could be overlap or even contain. Could be entirely within the IV estimates. And if you look at here, right, the confidence interval of the OLS estimate is actually entirely contained in the confidence interval of the IV estimates. Right. So statistically, we cannot tell whether they are the same or we cannot tell whether they are different. They are statistically the same, even though the point estimates are different. Second, look at the partial R square here. This already multiplied by 100, so they are actually very small, right? So that means the partial R squares are only about 0.01% or 0.04%. They are really, really small. Right, so like I say, if there's some small endogeneity in the quarter burst, those tiny R square, first stage partial R square, implies that the inconsistencies in the IV estimates could be larger than the inconsistency in the OLS estimate. And look at the F statistics here, right? So in column 2, the F statistic is 13, so it's larger than 10, but not too much. So it's greater than 10, so it's probably okay, but not by too much. But if you look at like the column 4 and column 6, the F statistic are only 4.7 and 1.6, so that's less than 5. And that means there could be substantial finite sample bias. Right? We say we probably want an F statistic at least greater than 10. These are even less than 5, and the last one is only 1.6. So we are worried about there could be some finite sample bias, which means the bias between education and the error could still exist in the IV estimates, and right, so the bias between the education and the error could still inside the IV estimate. They may not go away even though we have a huge sample size like 330,000 here. So to show that there's indeed there is indeed finite sample bias. So Bong and O, they did a Monte Carlo simulation. So what did they do? So they first create fake instruments. They generated randomly assigned quarter bursts. Because these quarter bursts are randomly generated, they have no predictive power, which means the two-stage least square estimate should be 0. If the asymptotic analysis is right, the two-stage least square estimate should be 0. If the bias goes away, then we should not see we should see the two-stage least square estimate to be 0, right? Because we know their probability limit is 0. So they did a 500 replication. However, what they find is that the two-stage. So they did 500 replication, and they find that on average, so the average estimate return to education is about 0.06%, which is almost the same. Which is almost the same as the IV estimate here, right? Which is almost the same as the IV estimate here that using the true quarter burst, right? So the fake instruments the estimate using fake instrument is almost the same as the estimate using true quarter burst, which implies that the estimate here could be entirely driven by finite sample bias, right? Because this guy, we know their probability limit is 0. They are not 0 because of finite sample bias, and the finite sample bias seems to be driving the results here, right? Because this is also 0.6. So if the asymptotic theory works well, the estimate from this randomly generated fake quarter burst should be close to 0. That's the probability limit. However, the sample size is still too small, and the IV estimates in Angus and Kruger are probably driven by the correlation between X hat, the education, and the U in the finite sample. Right? We know the linear projection and the error term is correlated in the finite sample.